Hi, in this video we are going to talk about the concrete implementation of the breadth-first search. So this is the first important graph traversal algorithm. With the help of this algorithm we are able to traverse all the nodes within the given graph. So let's implement a class node. It's going to represent the vertices or the nodes in the given graph. So it's going to have a constructor as usual with the init method. We have the self as usual and the name. So we are going to assign a name to every single node. Self.name is equal to the name. Then we have an adjacency list is equal to an empty list at the beginning. Sorry for that, it's a Y. And then we have a boolean visited, so self.visited is equal to false at the beginning. This is why we have to store a reference to this boolean, because we would like to check whether we have visited that given node or not. And we have a predecessor. Maybe we are not going to use this predecessor, it is equal to none at the beginning, but basically this is the previous vertex in the breadth-first order. And we are going to talk about shortest path algorithm, and we can come to the conclusion that with the help of breadth-first search we are able to find the shortest path. So basically Dijkstra's algorithm does a breadth-first search if all the edge weights are equal to 1. Whatever. In this section, we just consider graph traversal algorithms, breadth-first search and depth-first search. So what about the concrete algorithm? It is the class breadth-first search with the object. And we just have to define a BFS method with the self and the starting node. We have to define that what node we are going to start from. And then we have to get a queue. This is what we have been discussing in a theoretical section, that if we want to use breadth-first search, we have to use a queue as the underlying abstract data type. Okay, so first of all, we have to append the start vertex or the start node to this queue. So queue.append the start node. Okay. And of course we have to set this start node to be visited. So visited is equal to true. Okay, and basically the algorithm is quite easy. While the queue, what does it mean? That while the queue is not empty, we just have to get, so pop the actual node out of the queue. So queue.pop with 0 index, because queue has a so-called first in, first out structure. This is the FIFO structure. That's why we have to pop the first item we have inserted. Okay, then we have to print it out. So %s and actual node.data. Then we have to visit all the neighbors of this actual vertex. So for n in the actual node adjacency list, we just have to consider whether we have visited that given node. So if not n.visited, sorry for that, visited, we just have to set it to be visited. So visited is equal to true, and we just have to put it to the queue. So queue.append n. Okay, so basically this is how we append that given node to the end of the queue, and we keep popping the item from the beginning of the queue. Okay, this is why the queue has a so-called FIFO structure, first in, first out. The first item we have insert is going to be the first we take out here. And basically this is how we implement the so-called breadth-first search. For a breadth-first search, as you may recall, it is a layer-by-layer algorithm. We visit the root node, for example, this is the starting vertex. Then we visit all the neighbors of that A, so B, F, G. Then we visit the second layer, so all the neighbors of B, F and G. It is the CD, F doesn't have any children, and the G has the H as a left child. So we visit them. Then we go to the next layer. Depth first search, on the other hand, we will see is going to go as deep as possible on a single branch. So for example, for depth first search, we are going to visit the C or the E before we visit G and H. It's quite counterintuitive because G is nearer to the root node than the E or the C, but this is how depth first search works. On the other hand, breadth first search is going to go on a layer by layer basis. So we visit the neighbors of A, so B, F, and G. Then we visit all the neighbors for B, F, and G, which is going to be C, D, and H. Then we visit the E at last. Okay, so this is how breadth first search works. And I think it is a quite compact implementation. We have to use a queue as an underlying abstract data type. We use a list because in Python we can implement the queue with the help of a list. Then we have to append the starting node because we start there, and this is why we set it to be visited. While the queue is not empty, we get the first item we have inserted. This is the FIFO structure. We print it out, and then we visit all the neighbors of that given actual node with the help of the adjacencies list. If we haven't visited that given vertex, we set it to be visited, and we append to the queue. And again, this while loop is going to iterate until the queue is not empty. So let's see whether it's working fine. I'm going to have a node 1 is equal to node, for example, A. Then we have, for example, the node B, C, D, and E. So B, then C, then D, and E at last. We set the node1 dot adjacencies list dot append. We append the node 2. I'm going to copy and paste it one more time, and 1 and 1. Okay, we append the nodes 3, then 4, then 5 to the node 1, node 2, for example, and node 4. Then we just have to instantiate the breadth first search. So breadth first search, and we just have to call the BFS method, and we have to specify the starting vertex or starting node, which is going to be the A. So the A has the adjacencies list with node 2 and node 3, so we are going to visit A, and after that the neighbors of A, which are the B and the C, then the neighbors of B and the C, which is going to be node 4. Okay, sorry for that, I have to rename them 2, 3, 4, and 5, and then the node 4 is going to have the node 5, which is the E. So if I hit Python bfs.py, okay, we have some problem. Object has no attribute data. Sorry for that, I'm not going to print out the data, but the name, whatever. Let's see whether it's working fine. A, B, C, D, E. Okay, it's going to end up with the breadth first order. This is what we have been expecting, and this is how breadth first search works on a layer by layer basis. So it's quite compact to implement it, we just have to use a queue. It is quite a common interview question that for breadth first search we use a queue. For depth first search we could use a stack as an underlying abstract data type, but usually we implement it with recursion. You may come to the conclusion that okay, it is the same, and you are right, because recursion in the deep level under the hood is going to use the stack of the operating system. So we don't have to use a stack, we just have to call that method recursively, and the operating system is going to use the stack memory in order to calculate the depth first search. So no matter what, a stack is going to be used, but sometimes we can use a stack like a queue, sometimes we implement depth first search in a recursive manner, but what's quite important that in the background, a stack is used no matter what. So that's all about breadth first search. Thanks for watching.